Guys?
Thanks.
Ready? Yep.
Cool. Hey, everybody. My name is Grant, and this is Tyler. Today, we're going to be talking about Warner's kernel version for Windows kernel fuzzing for mere mortals. Cool. So Tyler and I are security consultants for NCC Group. We're both based out of Seattle. Woo! We enjoy native, low-level stuff, reverse engineering. We do a little bit of everything, kind of what we're asked to. So we'll take a look at web and API and code review. Cool. So some of the motivations behind this talk, we were interested in how the kernel works. We want to kind of share that interest with other people. We want to make sure that people who have not seen this before have kind of a bite-sized introduction to what we're looking at so that if you want to do this later on your own, you can. Cool. So some of the key takeaways that we hope you take are just a glimpse of how we do things. We don't have enough time to kind of go through everything in detail, but hopefully we leave you some motivation to learn more of this stuff. So a small caveat here. This shit is hard. It's technical, it's complex, it's low level, it's really deep, and we don't have quite enough time here to talk about everything, but we're going to give you as much as we possibly can, and we're more than open to questions afterwards too. So the kernel, the why and the what. So show of hands, how many people are familiar with the kernel? Awesome. And the fuzzing process? Awesome, great. So what is the kernel? The kernel is the heart of the operating system. This is the software that manages computer memory, I/O, scheduling. If you move your mouse across the screen and you wonder like, hey, what does that? That's the kernel. So why would we want to actually start targeting the kernel? Well, they're not going anywhere, and they're a relatively unexplored attack surface compared to userland. So it makes it kind of a juicy target. Finally, any crash is technically a denial of service because you're going to see a blue screen of death. So before we begin, consider the following. We're going to be fuzzing drivers that run in kernel land. So in user land, if you have a process that crashes, then the kernel is going to kind of take over. It's going to manage the memory. It's going to make sure that you get an error message back, and it's going to do so gracefully. But if you see a crash in kernel land, it hits the fan, it goes, I don't know what to do, and the entire system crashes. That's why you see a blue screen of death. So we need a way in order to figure out what happened if we do cause a crash in kernel land. And so how can we do that? And the answer is kernel debugging. So Windows has a tool called WinDBG or WinDebug that allows you to kind of take control of a kernel of another machine so that you can run instruction by instruction, use kind of like a user mode debugger. So you're gonna have two computers sitting either next to each other or on the same physical machine using VMware or some sort of virtualization software. And you're gonna have one machine, your host is going to be running the debugger and is going to be controlling all execution of our debuggy. So kernel debugging, or the debugger itself, is kind of this mandatory tool that we need to have so that we're not stuck with static analysis when it comes to analyzing the crashes that we find. So the tools of the trade for this process, first we're going to need a debugger. We're going to be using WinDBG. It's publicly free, available online. Awesome. Number two, we need an actual fuzzer. We chose to go with a fuzzing tool called DIBF. This is publicly available. It was written by some of our coworkers. So whenever we have problems, it's awesome just to be able to hit somebody up on chat and say, hey, why is this working the way it does? What exactly broke? Also, we're going to be using a disassembler such as Binary Ninja or IDA. This can be the free version here. So all this stuff is online, publicly available, and free, which is good news for all. Finally, we're going to be using WinObj and the Microsoft documentation extensively if you really dive into this project. So we're going to talk a little bit about setting up the debugger. This is going to be kind of the slow part. Sorry in advance. So we're going to be using WinDBG. WinDBG has two kind of options that you can use. One of them you will use. Serial debugging is legacy, it's old, it's slow, and you're not going to use it. You're going to use KDNET. KDNET stands for kernel debugging over the network. Cool. So I'm going to kind of go through the steps on how to set KDNET up so that you can do this on your own. So first, you're going to find two modern Windows machines. They can either be on the same physical hardware or they can be sitting next to each other. You're going to have one be the host, or that's running the debugger, and one's going to be your debugee. The debugee is going to be running the fuzzer and is going to be crashing. So when we run the fuzzer, hopefully we get some crashes in kernel land. Those will cause the debugee or a guest machine to crash, and the host that is running the debugger will be the one taking control of what's happening. So in order to set up this connection, we need to establish a network connection between the machines. Then we're going to create a debugging key on the guest that we're going to pass to the host. Then we're going to reboot the debugee. And if everything has gone correctly, then the kernel debugger will break in. So setting this up on VMware, there's only one additional step that you need besides if you were going to use two physical machines. And that is you need to set up a host only or private network in between your host and your debugee or your guest. Then you're going to log into your guest, whether or not it is virtualized or not. And you're going to run this command bcd edit debug on. What this does is it enables kernel debugging. bcd edit has an array of options that you can use that do a whole bunch of complex things. I'm not going to talk about them at all. I'm just going to use this to enable debugging. You can also check to make sure that you've done this correctly by running bcd edit without any command line options. Cool. So on your guest machine, you're going to go to the internet and pull down WinDBG, and along with it is going to come KDNET.exe. So on your guest, you're going to run KDNET.exe, and you're going to specify the IP address of your host machine and the port 50,000, which is the kind of the standard port for kernel debugging. If you run this, then it will give you a key that you're going to use on your host machine's WinDBG. So you're going to copy this key and open WinDBG on your host, enable kernel debugging, and slap the key in there. Cool, so we're almost there. Once you have this connection set up between the two machines, then you're going to enable verbose mode, and you're going to tell it to break in on the next boot. Verbose mode will let you know the second that your driver has been loaded, and breaking in the next boot will let you know that the connection has been set up correctly. So the pro about using KDNET versus serial, which we didn't mention at all, is that it is significantly faster. The only con here is that you have to have a compatible network card. Luckily, Windows has a huge list of compatible network cards. Chances are, if you're doing this, you already have one that is compatible. And if you don't, I can't help you. Cool. So we made it through the boring stuff. We made it through the setup. We're able to get on to more of the fun part. So just a quick recap. We have one computer, our host, is going to be debugging, have WinDBG set up, and our guest is going to be actually fuzzing the drivers and hopefully causing crashes. So now we're going to be on to the fuzzing process. So how do you speak to a driver? The main interface that we're going to be using are called IOCTLs, or input-output control codes. So the way that we are going to, the process kind of goes like this. First, we need to open a handle to the device that is correlated to the driver that we're going to be fuzzing. Then we're going to start sending IOCTL codes from userland that the device driver will receive. Each IOCTL calls a subroutine of the driver. So you're kind of telling the driver, this is the function that I want to call in kernel land. It will do something with it and respond back to you. This is the Windows API that we're going to be using in order to send IOCTLs to the driver. It's called DeviceloControl. And if you take a look here at the parameters, the second parameter here is IO control code. That is the actual IOCTL that you're going to be sending. Along with it, you're going to send an input buffer that's going to be filled with all of our fuzzing data. We also pass it input buffer size, which should be ringing security flags because sometimes drivers don't check that the size of what you sent them is actually the size of what you sent them. And we're also going to optionally provide an output buffer. And what this does is it allows the driver to fill in information and send it back to you when it has finished the process of the IOCTL that you've specified. Cool. So DIBF, our fuzzer, takes in a device name, which is correlated to our driver, and optionally takes in a list of IOCTLs to send to the driver. So the problem here is that IOCTLs are rarely, if ever, documented. Fastest way to find out which IOCTLs are valid for a particular driver is usually just to brute force them. So just start sending codes from 0 up to FFFF, see what the driver responds with, and figure out whether or not those are valid IOCTLs. Luckily, DIBF does all of this for us. And it is also a pretty good fuzzer in its own right. Cool. So in order to start using DIBF, we need to find the name of the device that corresponds to the target driver. We need to verify that it's actually present on the machine using WinObj, and then we're going to pass this information to DIBF and let it rip. So to go into a little more detail about this process, I'm going to pass it off to Tyler.
All right. So actually what I'm going to do now is I'm going to do some demos. So hopefully these will work okay. Let's see here. All right. Okay, cool. So what we're doing here is, we're doing the first step that we just discussed, which is finding the name of the device that corresponds to the target driver. So typically when you load a device driver, it's going to create this like abstract OS object called a device. So that's the thing that you need to open a handle to in order to actually make IOCTLs, or IOCTL calls, I should say. So what we're doing here is we've taken an example driver. In this case, this is called the HACSYS Extreme Vulnerable Driver, which is a driver that's specifically meant to give people practice doing like kernel exploitation stuff. Also, because we didn't want to pick on any like specific manufacturers and be like, look at these, we're going to fuzz this guy's stuff. So I've opened it up in IDA. This is actually IDA free. So basically, you can do this in IDA free. I assume it would work just as well in Binary Ninja. So what we're going to do here is we're going to go to the imports tab of IDA. The purpose of why we're doing this is because in order to create the device object, so there are several ways to do it. There are several different Windows APIs that you can call to create the device. All of them happen to have the word device in them. So if you go to the import section, which essentially tells you all of the Windows APIs that are going to be called by your driver, and just search for APIs that have device in the name, then you're going to find the one you're looking for. So at the bottom, which you may not be able to see, I'm typing device, and then suddenly there are two things in the list here: IO delete device, IO create device. As you might guess, IO create device is the one that we're interested in. So we're going to look at places in the driver where this function is actually called. We're going to use the cross-reference feature here. And we're going to see there's only one instance of it actually being called, and that's in the driver entry. Which is the function that's called when a driver is first loaded. So I'm going to pause it right here. So what we see right here is I'm mousing over this string that's being passed as an argument to IO create device. You can see pretty clearly it's passing the string /DOS devices /HACSYS extreme vulnerable driver. So basically from this we can deduce pretty clearly that that is the device name right there, the HACSYS Extreme Vulnerable Driver. So what we're going to do is, just to double check that this actually is the correct name, we're going to open the sysinternals tool called WinObj, and we're going to look through the list of devices that are actually currently present on the machine, and we're going to see if it's there. So you got to launch it elevated. I'm going to go to the the device section on the left here, and I'm going to scroll down. Scroll down to the H section. And there it is. So okay, so what we get from this is we know that this is the device name. So essentially, this is the device name that we're going to pass to DIBF later. So this is like our entry point for how we actually start fuzzing this driver. So that is demo number 1 of hold on a sec. That is demo number 1 of 3. So. Oh God, hold on. All right, cool. So here is demo number 2. So this one is pretty straightforward compared to the previous one. What we're doing here is we're just we're going to load this up in, so we have a command prompt. What's going on here? Oh yeah, okay. So we're starting DIBF, and we're passing it the name of the device that we just found in IDA. So now you see a bunch of output spitting out. I have it in verbose mode just to show, like, here are the IOCTLs it's trying. So you might not be able to see this, but it says found IOCTL, and it had like a list of about 12 IO codes. So at this point in DIBF's execution, if you just press Control-C, like if you think, okay, yeah, I don't need to brute force anymore. If you press Control-C, then it'll start just fuzzing these, and you may very well start finding crashes at that point. So essentially, at this point, arguably, you are kernel hacking at this point, depending on your definition of it. Let's see, and for the third demo, okay, so for the third demo, so the previous two demos, these were both being shown from the perspective of the debugging target. So this is the machine where we're actually doing the fuzzing. This is the machine that's going to blue screen if we find an actual bug, right? So what we're seeing here, like in opposition to the other ones, is this is the machine that is running the kernel debugger. So here, what we're going to do is we're going to show the debugger at the time that we hit a driver crash on the debugging target machine. So I don't know how readable the text is going to be, so I'm going to read this stuff out loud pretty verbosely. Hopefully Windows Media Player actually will cooperate and play. So it's going to sit here for a couple seconds, and then suddenly we're going to get a thing that's like, hey, you crashed. Yeah, okay, here we go. So I'm going to actually walk up here. So what we see is fatal system error and a particular bug check code. And then below it, we see driver at fault, HEVD.sys. So HEVD stands for Hacksys Extreme Vulnerable Driver. So we know that the driver that caused the crash pretty much is the exact one that we expected to have crash in this situation. So it lines up with our expectations. So I'm going to continue. Okay, so we know we got a crash, right? So we know we got a crash here. What we want to do next is try to do at least some basic debugging to figure out what happened. That's sort of like the interesting part. Like if you have an exploitable bug, then you can come up with a kernel exploit and do nasty stuff with it. I am not going to pretend to be able to teach you how to like debug kernel crashes in the space of like 5 minutes. It's definitely an art. It's definitely something that we could do like hours and hours of talks on. So I'm just going to give like extremely bare bones information about what you could do, just to get enough information to figure out like exactly which IOCTL is causing the crash, and what the input buffer was that causes the crash, so that you can repro the bug as much as you want, and then kind of dig deeper from there. So the first thing we're going to do is look at the call stack using this command K. The call stack is a little bit messed up. I'm going to kind of gloss over the details of why it's messed up. But long story short, I need to fix the debugging symbols. So I'm going to run this command called .symfix, which fixes the debugger symbol loading path. Then .reload to reload the symbols. Now that the symbol path has been fixed, now we're going to look at the call stack again, and now it's actually readable. In particular, down at the bottom here, you can see that the name of the user mode process that was executing code at the time that the machine crashed happened to be called DIBF, which again is exactly what you would expect because that's the fuzzer that we're running. So what we're going to do is we're going to take a look at this bottommost stack frame here. So we're going to click on, you might not be able to see it, but this number 15 right here, this is like the lowest stack frame of DIBF execution. So I'm going to click there, and it's going to show us all of the variables that were present in that stack frame, what their values were. So then we can look at info. So you may not be able to see this. If you click request, it's going to show you the contents of this IO request variable, which includes right here the actual IO code. So basically from this, you know exactly which IOCTL was responsible for the crash. So that's like important piece of repro information number one. And number two is the inbuf, the input buffer that was being sent to this particular IOCTL at the time of the crash. So I'm going to continue here. And if we just click on inbuf and do a little bit of WinDBG stuff, which I'm not going to talk about in detail. And there we go. So what we see here is the actual contents of the buffer that was being sent to the IOCTL at the time of the crash. So it's basically all zeros, except there's some Fs near the top. So actually not particularly complex input. This is a driver that was specifically written to be very, very crashy. So I guess it's not super surprising that you send it like a couple Fs and then everything else is all zeros and then it just falls over. So those are the 3 demos. So let me close out of this. All right. So just to recap the general process of using an IOCTL fuzzer, whether it be DIBF or another fuzzer. Step 1 is you have to figure out the device name of the device object that corresponds to the driver that you're trying to fuzz. Typically, you're going to find that through looking through IDA, or maybe you can go in WinObj and look through the list of devices and find something that looks related to your particular device. Like in our case, we were testing the Haxis Extreme Vulnerable Driver. So if you just scroll through the list of devices, there's a thing that says Haxis Extreme Vulnerable Driver. So in that case, like you don't really need to open in IDA. Step 2 is, again, if you were doing this analytically through IDA, then check in WinObj that the name is actually correct. The name is actually what you think it is, and then pass it to DIBF and let it go. I already did that demo and that one and that one. Oh yeah, okay. Recap. So you open handle to the device. Next one is you test specific IOCTLs. Or you figure out which IOCTLs you want to test. So here we're doing this mostly by brute forcing, by just trying every value from 0 to 8 Fs and seeing what the kernel tells us. Like, was this a real IOCTL? We just had an invalid argument being sent, or is this like, no, this is not a real one, go away. You can also find it analytically. We have a little bit of extra time, so we have a little add-on demo that shows in super basic terms how you could start analytically finding IOCTL codes. But long story short, you need to find which IOCTLs you want to brute force. And then number 3, of course, is you send garbage data to these IOCTLs to fuzz the driver. Here we got a little slide on sort of like some places you could go to get additional information about debugging and reverse engineering. Again, like I said, this is very much an art, something you put a huge amount of time into. From the point that you get a crash, then that's sort of like when the real fun begins. And frankly, like once you hit that point, then you may be in for much more effort than sort of like just the fuzzing part. So we have these 3 books. Either I or Grant or both of us has read all of these, and so we recommend these. First one is Reversing Secrets of Reverse Engineering, good for general reversing knowledge for x86. Practical Reverse Engineering, which gives specific reverse engineering information for x86, AMD64, and ARM. Also gives a little bit of Windows kernel specific information, as well as some information about using WinDBG. And then this third one, which is one that Grant is a fan of, called A Guide to Kernel Exploitation Attacking the Core, which is talking about kernel specific exploitation, not user mode programs, but specifically in the kernel. So with that, I will pass it back to Grant.
Cool. So when you go through this process, you run into trial and error. And we've run into a lot of trial and error. We kind of wanted to share those trials and errors with you so that you can, number 1, laugh at us, and number 2, not do these yourself, just like a lot of good advice in life. So noob mistake number 1, fuzzing with breakpoints on. If you have any information or have any use with a debugger, you know how stupid this is. Breakpoints essentially stop the execution of a program the second that you hit that point or that particular instruction that you chose to break on. So if you leave all of your breakpoints on while you're fuzzing, if your fuzzer accidentally or purposefully hits one of these code paths, then it's going to stop completely. It's not going to continue fuzzing. It's going to return it's going to break and wait for the user, that's you, to do something with it. So if you fuzz with breakpoints on and you actually hit one of those breakpoints, you're going to have a bad time. You're going to come back the next morning hoping and waiting for crashes and dumps, and you're going to end up with, hey, you hit your second breakpoint that you forgot to turn off. Number 2, I think everybody can get behind this one. If you have a machine that doesn't have any power, then you're never going to be able to fuzz anything. This is really compelling stuff here, guys. So make sure that your computer's plugged in to the wall, because if it's not, it might die overnight, and then you might run into a problem where you look stupid. Cool, next one. Windows Firewall can be a bitch. It will get in the way of your machines talking to each other. So if you don't want to bash your head against the keyboard for 15 to 37 minutes, make sure you add your exceptions for your Windows Firewall. Fun story, I was trying to set this up and ended up having to just turn off my firewall completely on a private network, of course, and to figure out that this was actually the problem. Cool, this next one is a little less obvious, fuzzing without driver verifier. So verifier is a tool that you can use. It's kind of like Valgrind. What it will do is it will detect weird memory accesses and will crash immediately. So there have been times where we were fuzzing for 12 hours on the same driver with nothing. The second we turned on driver verifier, it crashed instantly. So verifier is a very good tool to turn on. All you have to do is open up an elevated command prompt, type in verifier, and then you can see some of the things that it does for you is it will create a special pool. It checks IO verification, a lot of really fun stuff that is kind of out of scope for what we're talking about right here. Cool. So we are going to go on a little bit further about finding how to actually find the IOCTL handler in IDA. This will be helpful once you've found a crash and want to find exactly which IO code caused it and what it's correlated to, so you can continue your triaging process. But before that, we just want to give a shout out to some of our NCC folks. Some of them have moved on to better places, not heaven, but you know, other companies. So thanks to these wonderful gentlemen for all their support. And then we're going to give you a little bonus. So to talk about this, I'll pass it back to Tyler.
All right. So earlier on, we mentioned that you can find IOCTLs by just like brute forcing, or you can find them analytically. Let's see if I can get this to show up on the correct monitor here, and then get my mouse pointer on the correct monitor. All right. So what I'm doing here is I have opened a driver in IDA, and I'm going to just analytically in IDA try to find the IOCTL handler. So essentially what I'm doing here is I'm going through the list of functions in the binary, and then just looking at the graph overview section here, and looking roughly at the pattern of it. So you can see these are mostly linear. Like there are some if statements where it splits into two blocks, but other than that, they're like not super complicated. If we just keep rolling through these, we're eventually going to get to one that stands out like pretty clearly. You'll know when we get there. There it is. Yeah. So it looks like this. So the graph overview looks like this when you have like a whole bunch of if statements, or you wrote C or C++ code that has a switch case statement in it. So this is like a dead giveaway that this is an IOCTL handler, because it's doing stuff like check the IO code that was sent to us on this call. Is it this value? No. Okay. Is it this value? No. Okay. Is it this value? And that's typically implemented inside a single function. So usually an IOCTL handler is going to look like this, no matter what you do, unless you specifically like factored out parts of the code to make it not look like this. Also, another thing. Let's see. Is it still playing? It's paused. All right. So another piece of it is that if you look, this may not be visible from where you guys are, but in the code, typically the if statements are using these immediate values. Like there's some value that's like 88883020, 88883040. Like when you have these 4-byte values that are like all close to each other, that are all being used in if statements, again, that's a dead giveaway that those are probably IO codes that are being checked for. So if you like, you can kind of bypass the brute forcing process entirely by actually searching for the IO codes through a disassembler, but it's pretty much up to you, whatever you'd like to do. I'll let you do that.
Cool. So one final note here is that each of these IO codes are invoking a particular subroutine. So this is where we will go back once we have our crash and we've discovered which IO code actually caused the crash. We're going to head back to this function in IDA, and we're going to trace exactly which IO code we hit that caused the crash. And then we're going to continue down the code graph, and we're going to see a subroutine that particular IO code is associated with. And chances are very high that exactly somewhere in that subroutine is where the crash occurred or where the driver started to behave badly. All right. Cool. Sorry. Sweet. So that's all we have for you for today. We are happy to answer some questions. Sure, up front.
So is there a way we can get this PowerPoint videos after?
Yes, we'll be posting them probably next week.
Cool. So yes, we will. We'll make sure to share all these slides with you. Sure.
So can you give an example of somebody's driver that you actually were able to write working exploit code?
We cannot.
Not naming names.
Well, no, not specifically their company, but like the type of a driver and what you were able to do with it. Something more generic.
So a couple of our coworkers have done a process similar to this, and they were fuzzing Lenovo power drivers. They created an advisory for it. All these have been patched before. What they determine is that they can cause a denial of service and can cause kernel memory to be leaked from user land, which is bad. It can help you bypass KASLR. It's usually just a bad idea. There's usually a separation between kernel land and user land that we want to make sure maintains intact. Oh, did they?
I thought they did.
They had an arbitrary read write in the kernel space. One of the fun things about fuzzing power drivers is that your screen starts flickering in weird ways. You can create a kind of rave with your own laptop. Cool. Anybody else? Sure.
Done any automation of your IDA analysis or anything like that? So is there anything like directly on some of this functions?
No, we have not added anything to automation of this process. That is that actually leads me straight into it. That's awesome. There are some things that we still need to do moving forward. Some of the stuff that we would like to have happen includes that automation process of some of these bugs, as well as we'd like to add some functionality to DIBF. Some of our ideas include checking the output buffer for addresses that look like they're kernel addresses. Also, we want to make sure that once we have a crash, we can continue fuzzing from exactly where we were. Currently, we need to restart the entire fuzz run if we do find a crash. So a part of the automation and those features are going to be V2. We don't have them currently right now. Sure.
So do you have anything to fuzz plug-and-play drivers? This seems to be a legacy driver. Like, do you have anything to enumerate the interfaces exported by plug-and-play drivers into?
So we use the Hax's extreme vulnerable driver in this case for just for example. Ease of demoing. So there are drivers that are you can just start ripping right out of the box. As soon as you plug in the device or whatever it is associated with, it will create a device on the machine that you can identify very easily, and you can start going ahead right away. Sometimes the actual device that you need to pass to DIBF is obfuscated, or you actually do a little more digging in order to find out what that is. I will say just on top of that it's probably best to target drivers that were not written by Microsoft, just because although they are a good target because they're on all Windows machines, they've been beaten up. They've been attacked quite a bit. So if you are curious about kind of doing this own process and having it be fruitful, it's probably best to look after drivers that are not directly written by Microsoft. Does that answer your question? No. Cool.
And one more quick note regarding the link that we're using, right? Like that is a symbolic link, not a device link, right? Because like in the WinDBG, when you're looking at it, the main, right? The way in which they're using it.
Symbolic link.
My question is that is actually a symbolic link, not the device link.
That's absolutely right. That's true. We didn't have quite enough time where we thought we didn't have quite enough time to elaborate on that, but you're absolutely right. Sure.
The fuzzing seems to be focused on
on the drivers in the Windows environment. Have you or yourself or are you aware of anybody turning this kind of technique onto something lower like UEFI or an option realm of a PCIe device?
Do you? I don't. No.
Wouldn't be surprised.
True.
I'm sorry?
He said that we would not be surprised. But we do not have any experience with that personally. Cool. Please catch us afterwards if you have any more questions. Let's go party.